All right, so Unit 2 is all about differentiation. I added a couple slides on this as well, so definitely pay attention. Again, this is just an overview, sneak preview of everything, and then we're going to focus more on 2.1. This is how I want you to frame the entire unit. It's based on this concept, the slope of 1 point. All we're doing is trying to find the slope of 1 point, or a formula that finds the slope of 1 point. Okay? The reason why that's important, like in real life, is the way I explain it is, say you were driving 50 miles, so point A to point B. You're driving 50 miles, so like close your eyes, imagine going from point A to point B. It's 50 miles. Probably not going to be a straight line if you're imagining in your head, but maybe you are imagining a straight line in your head. Now, if it took you 1 hour to drive those 50 miles, what is your average rate of speed? I shouldn't say that. What's your average speed? 50 miles per hour. On average, you were going 50 miles per hour from point A to point B. I said it was 50 miles, and you did it in an hour. Now, does that mean you were going 50 miles an hour in every single instance during that trip? No, probably not. You were probably not going 50 throughout because you had to stop, you had to turn, you had to do all this other stuff during it where it messed up your speed a little bit, okay? Well, the average speed, that's algebra 1. That is slope, that's old school math. Calculus is when a cop is shooting a radar gun at your car, his or her radar gun at your car, that's the instantaneous rate of change. That's your instantaneous speed in that instance in time. Okay, now it's kind of a, I don't know, like a misnomer because you can't have change at an instant, because if you imagine like pausing time, if you pause time, how can you have change? Like if you're driving in a car and then all of a sudden you stop at an instant, you're not moving anymore. So how can you have instantaneous rate of change? Because of limits. The limits allow that to happen because you're getting infinitesimally closer to an instant in time, but you're not actually, it's not an actual instance in time. But the radar gun essentially is what calculus is. It's your speed exactly in that moment. And that's what this is. The slope of 1 point is that change, that rate of change in that one instance in time. That 1 point right there where it says slope, question mark. Okay, that's kind of how I want you to frame everything. Now, in rates of change in an instance are super important if you're going to be an engineer, or if you're going to be a chemist, or if you're going to be a physicist, or if you're going to be a business person. I'm trying to think of anything where they look at rates of change at an instance. Because certain things, you know, like say you're building a bridge. I always use that as an example. You're building a bridge. If there is a certain rate of change of the wind speed or the temperature, it could throw off the bridge, where in that one instance in time, it makes it so the bridge just collapses on itself. Okay, so you have to take into account, you have to model the bridge before you build it. They don't just build a bridge and go, I hope this works and nobody dies. They do all the math up front. Because if it breaks, you just wasted a ton of money paying all those people to do all the construction and all that other stuff. So you have to like analyze every little variable for engineering or physics or whatever it is to make sure that whatever you're trying to study does work that way. Because if it didn't, that would be a problem. So that's why they force you to take, you know, up to Calc 4 if you're going to be an engineer, or one of the physical sciences, because that kind of stuff is super important. When I was a chemist, one of the things we looked at was reaction rates. If you've taken AP Chem, you've done reaction rates, is right? Correct? Anybody taken AP Chem? People at home? I think yeah, I know you do because I taught the class. There's reaction rates in there. You can use calculus on those reaction rates. Okay, like rates of that a reaction occurs, essentially. Now, why is that important? Because if you're given a cancer drug, you want to know how long it takes for a certain reaction to happen. I worked with cancer drugs primarily, but you need to know how long a certain reaction happens, because it might have a byproduct. It might digest a certain way where the medicine's not as helpful for whatever it is. So all that stuff has to be looked at. So that's why this is hugely important, even though it's a super simple concept. Just the slope of a point, but the ramifications of it, it's crazy. Now, I wish this class was kind of taught that way, where it was more focused on real world stuff, rather than, you know, having a contrived problem like this. Like, that is no inkling of anything related to the real world at all. You know, it's just a problem that somebody made up, AP made up, but it's not really related to anything. The concepts are important, of course, but I do have to teach this. Again, that one student that said, I don't like the curriculum for AP Calc, we're shackled to this. I have to teach it with all these, you know, problems like this. But eventually in Unit 3, we are going to get into the more realistic stuff for how this is used. When you're going to be an engineer or a scientist, you're going to be using a ton of calc in those classes as well. This is just an intro, but that's a big deal. in my opinion. And again, if you don't think that's cool, then I hope you're not getting into like engineering and physics and chemistry and those kind of classes, because you should think it's cool if you're really interested in that, unless you're being forced to major in something like I did when I was a kid, where my mom made me, or my dad made me major in something. But hopefully you think that kind of stuff is cool, because it's a huge thing. The rates of change of something, huge, especially at an instance. And I've taught this for 7 years, 8 years now. Like, I'm still like, it's just crazy. I don't know, love it. And this was invented in 1687. We're still studying it now. It's just insane to me. Sorry. All right. Essential questions. We already talked about that. You should be able to answer all these by the end. I'm not going to worry about it so much right now, but like question 1, 2, 3, you should semi be able to answer a little bit by the end of today. Okay. If not, you might already be able to answer them. All right. So yeah, we're going to focus on 2.1, secant lines, tangent lines, differentiability, and estimating derivatives at a point. Okay, secant lines, tangent lines based on 2 points, tangent lines based on 1. And it's just skimming, it's just grazing that point that it's based off of. Okay, that's what a tangent line is. Slope of a secant line, this is old school. You should know this already. Change in y over change in x. And then we have the limit definition of derivative. Okay, and all the other notation. 2 main people were the ones that created calculus, so the notation gets a little crazy. For example, this dy over dx, d is not a variable. I look at it as like a delta, like delta y over delta x. You know the triangle, do you guys know what I'm talking about with deltas? Okay, so d is not a variable. You might think, oh, the d's will cancel. It's like, no, it's actually just change in y over change in x. It's just change in y in an instant. Y prime, this y prime, what that means is the derivative of y. F prime of x is also the derivative of y. And it's all based on this equation right here, the limit definition of derivative. Okay, it is still a change in y over change in x. I'm going to show you, I'll just show you why really quick, because some people might not actually see why this is change in y over change in x right away. Okay. You do not need to write this down because it's very basic, but so this should be pretty self-explanatory that like this is like maybe a y1 minus a y2 right here. So like this might be y1, this might be y2, but then how the heck is this thing x1 minus x2? Does anybody know? Someone's got to know. You guys are just being shy. No? People at home? The answer is actually right in front of you. This right here is your x1, and here is your x2. So you're doing x plus h, I'm going to put it in parentheses for no reason, minus x. So when you do this, you'll notice the x's cancel, so you have an h on the bottom. Okay, but it is still change in y over change in x. It just doesn't seem like that because there's an h on the bottom. It's because it's simplified all the way. Does that make sense, everybody? Good with that? Okay, cool. All right, alternative definition. Okay, this is an AP concept. It's not covered in regular calculus, so you do have to know this. I apologize ahead of time, but it's actually easier to look at because it is change in y over change in x. If you notice this equation right here, there we go. It's y1, the f of x, minus y2 is f of a, divided by x1 minus x2. The only difference too here is instead of h's, it's got an x approaching a. So the values at the bottom are getting infinitesimally closer. The values at the top are getting infinitesimally closer. It does mean the same thing as this though, with the h. Because the values at the top are getting infinitesimally clocer because the h is just that little nudge. It's just approaching 0. It's super tiny. And then it's approaching 0 at the bottom as well. So it is technically the same thing. 99% of the time they use this. Every now and then they give you a question like this, and I want you to see, oh, that's just derivative. Okay. A usually has a value, like let's just say it's 3, for example, in the one we did already. Then it would be f of x, or f of x minus f of, well, I shouldn't say f of 3 over x minus 3. Okay. A usually has a number in it. H is always going to be h. And it's always going to approach 0. Okay. The difference with this one is the x might have a value. This one will not have an x with a value. I mean, I guess it could. I shouldn't say it doesn't. All right, this weird symbol means second derivative, okay? And it's not d squared. That's what sucks about it. The notation is kind of, I don't know, not the best thing in the world. But again, it's because another person created the notation rather than just using Newton's notation. But really what this is based off of is the derivative. So d over dx is the derivative of the derivative. Okay, so it looks like it's d times d, so they put a d squared, but d is not a variable, so I don't know why they do it that way. Okay, and then dx times dx is dx squared, but shouldn't it be in parentheses? It drives me nuts. Is anyone else bothered by this? People at home are probably bothered. I don't know. All right. Your calculator will also do derivatives. Take your calculator out. I'm going to show you how to do this right now. This is pretty intense. All right, so here we go. Why is that there? Okay. So what I want you to do is let's just do an example of that we just did. Okay, so what I want you to do is hit Math 8, and it brings you up to this thing right here, which is awesome. If you have an older calculator, if you have a TI-83, it will not do this. It's going to say n deriv. Does anybody have an 83? I forgot. Oh, I will show you in a little bit. I'm sorry. So you want d over dx, because in this case, we're doing the derivative with respect to x. You can change that variable to anything you want, though. So say you were doing the derivative with respect to t or something like that. You could put a t in there. You can put whatever you want. We're just going to do an x for now. Okay, and then we're going to do the derivative of 2x. Okay, that didn't work. Hold on. 2x minus 4, because that was the second piece that we did in the piecewise. And we're trying to find the derivative at x equals 3. So we're going to put a little 3 in there. Okay, well, we already did this before, so you know the answer is 2. But if you notice, it does the answer for you. The one thing that it will not do is it will not find the general derivative. It will only find the exact derivative at a point. Your calculator will only find the derivative at a point. Now, if you have one of those Inspires, the CAS version, the computer algebra system, it's called, it will actually do the derivative entirely. Like, it won't just do it at a point. This one, you have to only do it at a point, so it does it at 3. So if I did something like this, everyone hit Math 8 with respect to x, and then we're going to do x squared in there, and we're going to do the derivative at, let's just do it at 3. The derivative of x squared is 2x if you use power rule. You bring the 2 down, you minus 1 from the power, so it's 2x. Well, x is equal to 3, so it's going to be 2 times 3. If you hit enter on this, you get 6. It will not spit out 2x, which would be nice. I do have a CAS calculator, though, if anyone wants to see it. And it's really cool because you can do the craziest derivative ever, hit enter, and it actually spits it out the exact, or the general, not the exactly at a point one. Okay. People that do not have a newer calculator, what you need to do, hold on, I'm going to turn this into classic mode so you can kind of understand how to do this. This is a lot of steps, so if you ever do forget, as long as it's not the final, I will help you. I don't care if it's a test or anything like that. If you do need help on your calculator, make sure you ask. Same process, people with 83s, Math 8, but it brings you this in deriv thing. Okay, first thing that goes in there is the function. So I'm going to put x squared in there. And then I'm going to do, let's just see, you have to put a 3 here and then hit comma, and then with respect to x. Okay, if you know anything about programming, that's a method, and then there's inputs to the method, and then methods are sort of like separated by commas, essentially. That's what that is. So that's what that is. If you hit enter, okay, I messed up the method. I'm sorry. It goes x comma 3. If that ever happens, just flip flop them, and then you get 6. Okay. So n deriv function, what you're doing it with respect to, and then what the x value is equal to. Okay, I would write that in your notes, or you can always ask too if you have an older calculator. The newer ones are awesome because they put it in the notation already, the derivative notation. So Math 8, x squared, 3, boom, done. Have a nice day. Now, it would be cool if you can graph derivatives because it helps you a lot in this class. So let me show you something that I showed AP. It literally blew their minds because they didn't know you could do this. So say I wanted to graph x squared. Put that in your y1. Okay, leave y2 blank. It'll make more sense later on, but leave y2 blank. and go to y sub 3. Okay. Now I want to graph the derivative of x. I'm sorry. I want to graph x squared, and then I also want to graph the derivative of x squared. So here we go. We're going to do math 8. We're doing the derivative with respect to x. Now I want to do the derivative of x squared, but I want this hard coded in. So if I change y sub 1, it automatically changes whatever's here. So rather than putting x squared in here like this, I don't want that. Okay, I want it to be where just whatever the y1 is. Because what if I wanted to make y1 x squared plus 1? I don't want to have to change it in 2 places. Wouldn't it be cool if I just changed it in 1 place and then it automatically changes my y sub 3? So what we want here, instead of putting the x squared in here, we want to put the y sub 1 in here. Okay, this is how you do this. Ready? Hit the vars button for variables. It's right here. You can see it on my screen. It says vars. This will work for anyone's calculator, by the way. Arrow over to the right, and it says y vars. Hit function, and then just hit y1. Now it automatically does the derivative of whatever's there. Okay, now this is what's crazy. This is like the trainer at the AP thing. I had to do a training for this to teach the class. Like her mind looked exploded when I showed her this. Check this out. If you just put an x in here, it doesn't make any sense. So it says x equals x. But the way the graphing utility works is it puts in x's at all the values that are on the screen so it can graph it out. So if you just leave it as x, watch what happens. Check this out. It graphs the original. There's x squared, but watch this. Here's 2x, the derivative. So it actually will graph it on top of it. This is hugely important later on. Maybe this unit, but mostly unit 3. I cannot stress that enough. So what I would do is never delete this. Never delete your y sub 3. If you don't want to use it, just turn it off by going to the equal sign and hitting enter. Okay? Now it won't graph anymore. So in case you don't want like the derivative to graph on top of it, but do not delete it. Okay? Because if you delete it, I'm never showing you how to get back to it. I'm just kidding. If you delete it, I'll show you. Okay? Keep it there for the AP test as well. Keep it there for every test in this class as well, because it helps you greatly. And I will show you specific problems later on that have you do this. But there's certain things where like you don't even do the derivative by hand. You can just use the calculator to do it and then have the calculator solve with the graph. It'll make sense when I show you an example problem, I promise. Okay, any questions on that? I'm telling you, this is a game changer. You'll see. It's insane. Okay. I also, let's put the second derivative in there just for fun. The second derivative means you do the derivative of the derivative. It's kind of like Inception. So put an x there. Now we want to do the derivative of y sub 3. So we're going to put a y sub 3 in there with respect to x. So now it's going to do the second derivative of x squared. So the first derivative of x squared is 2x. What's the derivative of 2x? Come on. 2. Thank you. So now watch. It's going to graph y equals 2. Look at that. That is amazing. Okay. All right. So much fun. So much fun. All right, let's keep going here. All right, 212 is all about differentiability. As I told you before, it has to be continuous. It has to be differentiable to be differentiable. If you're differentiable, you're automatically continuous. If you're continuous, you're not necessarily differentiable. The derivative has to match on both sides. So now I'm going to show you something that is going to make your mind explode. Maybe, hopefully, probably not. Oh man, I hope I didn't show this in a video already. Probably did. Okay, ready? Here we go. Watch this. If you're a flat earther, you're going to love this. Okay, so I'm graphing x squared. Okay, now I want you to imagine in your head, this is going to get insane. What happens if at the origin, I just start zooming in? Just zooming in a bunch. What is going to happen? Can you visualize that in your head, what it's going to look like? It's going to get wider. It's going to look like it's getting wider. Okay, I like that. What else? Does anybody else have anything else to say about that? Okay, here we go. We're zooming if no one's going to say anything.
Oh, it's a straight line.
Straight line. Who said it? Thank you, Jonah. Appreciate that, my bro. Okay, here we go. Check this out. We're zooming in. Look at that. It becomes a straight line. That's insane. Okay, this is also why the Earth feels flat, right? Because I could have easily graphed a circle here. Actually, couldn't I just do, I think they let you do polar, right? not. Oh, they do. Cool. Check this out. So say you're on Earth. Now the Earth is way bigger than us. It's like not even funny how big it is compared to us. So I'm not even doing this justice, but if you kept zooming in, the Earth is magically flat. Right? What happens if I did this? Let's do this. This last time. What if I did something like that? First of all, at 0, 0, does the derivative match at both sides? Okay, as you approach 0, does the derivative match at that sharp turn? If you had to draw a tangent line, would they match? You're saying no, why?
Because it would, wouldn't it be just a horizontal line?
Would it though? Oh, see, that's another here. Let's keep going with this. So I zoom in here, it becomes 0. Which he just said is a horizontal line. If you do the derivative, check this out. If you do the derivative of f prime of x, it graphs the derivative on the screen. At 0, the derivative is 0. And it is. If you saw what I just did, I zoomed in. Sorry, you just gave me the thought of the horizontal line. It is 0. This is called local linearization. Now, if I do it, let's just say I zoom in right here at 1. This point right here. Watch what happens. Oops, it's not going to let me do it easily. It still becomes a straight line. It wasn't just at 0. Now, what is the slope of this point? Can you see at this point right here? If you zoomed in? What? 2. Yeah, you can see it goes up 2 over 1. For these, you can't really see it very well on this. But if you notice, if you actually graph the derivative at 1, oops, it's 2. Okay, you can even write it over here. F prime of 1 is 2. Okay. Anytime local linearization happens, if you zoom in, it's differentiable because that means there's a tangent line that can be drawn on that. Okay, so you said it's a horizontal line for this one. Whoops, for this one?
Like a flat line.
Flat line? Flat horizontal? Give me more specifics.
Like that.
Okay, flat line. Anybody else say anything else? Jonah? You got anything? See, the interesting thing about this one, I'm just going to draw on this here, is that if you did a tangent line at this side, it skims it on this side, does that, but on this side, it skims it like this. See how it doesn't agree on both sides? So the moral of the story is if there is a sharp turn, it's not differentiable, but that still does not answer our question, what happens if I zoom in at 0? Not exactly intuitive to think of it this way. But if you zoom in, it ends up being a vertical line. What's the slope of a vertical line? As you approach infinity, but 1 over 0 is undefined, right? So check this out. If I do the derivative, whoops, at 0, it's undefined. Okay, it's a vertical line. Okay, if you zoom in and it happens, don't write infinity for the slope, even though it technically is kind of right. It's actually undefined. Okay, it's not differentiable at that point wherever there's a sharp turn. Okay, now check this out. I'm going to approach 0. That going to a specific value? Like it's going to infinity. Not intuitive at all. Okay, ready for the last one? Check this out. Let's do equals this. What happens if I zoom in here?
Oh, it's just going to stay up to it.
Yes, very good. Look at this. That's insane. Look at that. It's crazy. The derivative does not match on both sides. This is a positive derivative. This is a negative derivative. It's also a sharp turn, so if you want to look at it that way.
Is it because it's like no quote-unquote acceleration? You want to think about it like that? Like if you had a y equals x, it could also just be the same. Because it's not changing.
Yes, in a way you can think of it that way. Yeah, it's always positive 1 on one side, always negative 1 on the other. If you do the derivative, yeah, that's one way of looking at it. Okay, estimating derivatives at a point. To kind of show you this, because I was very abstract about it when I said if you can't find the derivative at a point, then just estimate it using values with slope. I'm going to show you that. I guess I can show you that now. So it says enduring understanding, derivatives allow us to determine rates of change at an instance. I've talked about that a bunch. If that's one thing you're going to remember in the next 10 years about calculus is that derivatives, instantaneous rate of change at a point. By applying limits, I've talked about that as well. The knowledge of rates of change over intervals. So the whole objective of this 213 here is estimating derivatives. So you should be able to estimate derivatives by the end of this. And it says right here, the derivative at a point can be estimated from information given in tables or graphs. Technology can also be used to estimate derivatives. Okay, I'm just going to shoot straight to the example problem right here. Estimate f prime of 7. Okay, and we have a table here. So to estimate f prime of 7, we can find the slope of 2 points that are on the outside of 7, where the 7 is in the middle of those 2 points. So what value should I use? What x values should I use to estimate f prime of 7? So it's right in the middle, right? And it's always like this with AP. They always say, estimate f prime of 7, and then there's a 6 and an 8. Estimate f prime of 3, the second bullet point right there, that's between 1 and 5. Okay, it will always be that way, where you can just pick the one, whichever one's in the middle. I want you to write this down now, so take out something to write with. But this is going to be one of the easiest things you do in the whole class. Estimating derivatives, I don't even know why we go over it because it's so basic. Doesn't seem like it's AP level. I feel like I could teach, Algebra 1 kids this. So what we're going to do is we're going to find the slope of these 2 points right here. So we're going to do change in y, which is going to be -7. Here, the y changed -7. And then change in x is 2. And that's it. Actually, I don't even know why I said write that down. That's all you literally do. Okay. If you were going to estimate it, that's what would happen. If you notice the y's go down as the x's go up, so that means it's going to be negative. Don't mess that up. Okay. So f prime of 3, same thing. We're estimating it. There's no equation for us to take the derivative of and plug in 3. So you have to use the 1 and the 5. The x is equal to 1 and x equals 5. Use those 2 points at 1 and 5 to find f prime of 3. So it looks like this one goes up and this one goes up. So that means you're going to have a positive slope. That's awesome. It goes up by 8 over 4. So you just do 8 over 4. This one's equal to 2. These are usually in the free response section of AP, of an AP test. Okay. Super easy. Okay. This one is actually from an AP test. This is an exact problem from an AP test. Right now, you should be able to estimate h prime of 6. But using the correct units, interpret the meaning of that might be a little bit more difficult. But we're finding h prime of 6 here. So let's just focus on this part right here, estimating it. So h prime of 6, well, 6 is between 5 and 7. So you're just doing the slope there between those 2 points there. So it's going up for both of them. So it's going to be 5 over 2. Now it says using correct units, interpret the meaning. That's actually unit 3, so we're not going to worry about that right now. We meet the meaning of that h prime of 6, but if you really care to know, it's going to be meters per year. It's the rate of change, the estimated rate of change between 5 and 7 years is, what did I get? What did I say the answer was? 5 over 2. 5 over 2 meters per second, or meters per year, I'm sorry. But we're not going to worry about the second part. But that's what it looks like on an AP test. So it's not like it's going to magically become harder on the test. It's literally what I'm showing you. This one right here shows the selective values, differentiable. By the way, it always has to say that it's differentiable, because if it's not differentiable, you might not be able to estimate the derivative. So whenever you see that, you can kind of ignore it. Okay. If it didn't say that, then you can say, no knowledge of whether it's differentiable or not, we cannot make the estimate accurately. But we'll always say that. It says estimate f prime of 4. Again, you would just use 3 and 5 for that one. It is a trick. You're not supposed to use this column at all. Okay, you can't just say it's between 8 and 3 for f prime of 4. You do have to use the 3 and the 5. Okay. Any questions on that? So it'll be 5 over 2 again. Yeah. Super basic, super easy. All right, differentiability. Let's look at some differentiability problems now. All right, differentiability. So it says right here, by the end, you should be able to explain the relationship between differentiability and continuity. The relationship is, if it's continuous and it's not a sharp turn, then it's differentiable. Okay. If it's continuous and a sharp turn, then it's not differentiable wherever that sharp turn is happening. Okay. It's kind of what it says right here. It says a continuous function may fail to be differentiable at a point in its domain. Again, with a sharp turn. This one right here, if a function is differentiable at a point, then it is continuous at that point. Okay, if it's differentiable, it has to be continuous because it never would have gotten that far to begin with. You do have to use that information sometimes on like some of these weird multiple choice questions. You'll be looking at it and go, I don't know, how am I supposed to prove this? Oh, and then you have to like think, oh, it's differentiable, so that means it's continuous. Since it's continuous, I can do this other thing. So just make sure you understand that it goes one way. If you're differentiable, you have to be continuous. But if you're continuous, you are not necessarily differentiable. And I have examples here that kind of show you. This red one is continuous and differentiable. There's no sharp turns. There's no holes, jumps, or gaps. Awesome. This one is continuous and not differentiable because of this sharp turn right here. Okay? I'm just going through every single combination. Impossible to draw a graph that is not continuous and not differentiable. Okay? And then this one right here, not continuous nor differentiable here at that point. It's not continuous, so because it's not continuous, it's not differentiable. You can't have it where it's not continuous but differentiable. So I feel like I wrote that wrong. Possible to draw a graph that's not continuous and not, this should be gone. That's embarrassing. So if I have something like f of x is equal to x squared, I just like using that example as x squared. Say I wanted to actually find here, let's do this. Let's do f of -1. Actually graph this though. Let's do -1 f of -1. So that's right there. Okay. Let's do 2 comma f of 2. Okay, let's label that right there. Okay, now what you can do is you can find the slope between those 2 points, right? That's the slope of a secant line. You've been doing that since algebra 1, finding the slope of those. Here, I didn't really set this up very well. Sorry, I'm not supposed to improvise. Ooh, shoot, sorry. Doesn't matter. Let me clean this up. Sorry. That's our m from those 2 points. I'm just going to put an m here. Let's do this. I want it right there. Okay, sorry, just getting the line to show up there. So the whole idea behind like finding derivatives is those 2 points are getting infinitesimally closer together. So we are going to get closer together on, let's just get closer together on the -1. Okay, so what we're going to do here is I'm going to say a is equal to -1. Do it with that, yeah, let's just do it based off that. All right, so we're going to say a is equal to -1. So I'm going to do y is equal to the, oh, I didn't do this very well. Sorry, just trying to do this. Hold on. Let me change this one. Forget this. Sorry, forget the a for now. Okay, check this out. So if I do -1 and put -1 in here, this is going to spit out. Actually, why is it? Oh, because it's still based off of f. Okay. Hold on. So we're going to do. Oh, Jesus. Sorry, this is so embarrassing. Yeah. Here we go. It shouldn't happen. There we go. Okay, that should happen. So what I did is I have -1 and f of -1. I'm going to get rid of this for right now. And get rid of the label apparently. So we have that 1 point there. And I'm making another point and I'm calling it a. But right now a is equal to -1. Okay, so it's just right over it, as you can see. Not very interesting. Okay, you cannot find the slope of it. It says undefined because it's 0 over 0. So what we can do, check this out. I'm going to make a get infinitesimally closer to -1. So I'm going to put a 0.1 in here. And watch what you'll notice. Oh, let me zoom in here. These points are kind of far away, but watch this. If I make them closer, now it's even closer. Put another 0 and they're even closer. Now, if I keep doing this, you'd really have to zoom in to see how far away they are. It might run out of memory. Hold on. Okay, nope, they're still a little bit far away. But check this out. If I zoom out, it looks like it's the tangent line essentially for that. So that's essentially what you're doing when you find a derivative. You are plugging in a value that's super, super tiny, super getting closer and closer. And really, it's getting infinitesimally closer. So, whoops. So I really should just be hitting 0 a million times here. We ran out of memory, so it got rid of the line. We have to go back to where it actually showed up. There we go. Let's put another 0 in there. So then if you zoom in here, what time is it? It's basically like a tangent line. I'm sure there's, it kind of crosses it weirdly, which it really shouldn't do. That should be grazing it. It doesn't really matter. It makes it a little bit better. And you have to really zoom in here to see the separation between those two lines, right? So that's essentially what you're doing when you're finding the derivatives. We're not going to be doing that though. We're not going to be doing the limits definition of derivatives. You're going to be using the rules for it. Okay, because if you did the limit definition of this, it would just take way too long, as I was showing you before. But and you could do this for anything. So say I wanted to do at 2. Okay, well, let's get infinitesimally closer to 2 on this one. So if I plug in 2 right there, oh, but this is still based on -1. Okay, if you notice the points are right on each other there, but watch, if I get infinitesimally closer to 2, by the way, I should be doing both sides on this. Because the slope is 4, oh, this is not changed to 2. I should have made a letter for this. Hold on. And you can see it's getting infinitesimally closer to it because I did 2.001. If I got rid of these, again, you'll see, there we go. You'll see it's getting closer and closer each time. Just have to zoom in each time. Does that kind of help make sense of the concept behind what a derivative is? It's technically still the slope of 2 points. You're just getting infinitesimally closer with those 2 points. And because you're getting infinitesimally closer, you're using limits, you actually are getting the slope of 1 point, even though it doesn't seem like it makes sense.